Let's talk about factoring. The word factor, remember, is just a part of a multiplication problem. So you multiply two factors together to get a product. You've probably done factor trees before, where you take a composite number, a non-prime number, and we want to break this down into its prime factors. Or what you're probably asked to do is find the prime factorization of this number. And yeah, so we just kind of split it up into a factor pair. Let's see. 24, I know, is 8 times 3. So we'll go 3 and then 8. And then when you find a prime number on one of these branches, I like to circle it. And then for any composite numbers left over, we break it down yet again. So this will be 2 and 4, because 2 times 4 is 8. And, 2 is a prime number. Even though it's even, it's the only even prime number. And then 4 can be broken down to 2 times 2. Now, we don't break anything down as, like, I could break down 4 and as 1 and 4, but 1 is a factor of everything, but if we're trying to find the prime factorization of it, technically 1 isn't a prime number. Then we would rewrite 24 as the same thing as, well, every time you see a prime number, we're going to raise it to that many of an exponent. So 2 to the third power times 3. We're going to use this concept in a way when it comes to our variable terms now. Yeah, let's do that. Let's take an example and let's prime factorize this. Might sound weird, but let's roll with it. Let's see where it takes us. Well, I know that this is 6x squared times y, like that. Just make it really easy for myself. Y by itself like this would be considered a prime factor. It's not a prime number because it's a variable, but it would be considered a prime factor of this term. So I'm going to circle it. Then I can split this up as 6 and x squared. Okay, both of these are considered composite, I suppose. That's not a prime factor of that thing up there. This will be 2 and 3, which are both prime numbers, and then x squared will just become x and x. Why am I doing this? This is a little obvious. This is a little less obvious, breaking down 24 as a product of prime numbers, but then these are just, all of the most basic factors of this term. I'm kind of trying to get you guys to remember what the GCF of a number is. Remember that GCF, when we were trying to reduce fractions down to lowest terms, we wanted to divide out the GCF between the numerator and the denominator to try and simplify it as much as possible. And that concept is going to be very similar to the concept of factoring. So, factoring is no different than the kind of reverse distributive property, in the sense that we're going to be dividing out the GCF of a polynomial, putting it into the form that we recognize as, we're going to distribute this. Give you an example. 5y. Now, what is the GCF of these two things? Well, it would be 5. All right, that's the only factor that these two guys have in common, so it just happens to be the greatest common factor. To put this into factored form, or I want to distribute this form, I'm going to divide out the 5 from both of those terms. So take 5 out, and then put in parentheses, okay, 5x I divided by 5. So 5x divided by 5 is just x. That plus is still separating these two terms, so it's going to separate the binomial on the inside. 5y divided by 5 is y. Hooray! We've factored this. It's just reverse distribution. Let's do something a little bit more complicated. These are not like terms because they don't have the same combination of variables. And I'm going to ask you to factor this. Well, I'm going to do it, but you would be asked to factor this. What's the GCF of these two things? Well, they both have a 5, and they both have an x. We're going to divide out that GCF. The method I like using is taking each part, each factor, each constant, and then each variable separately. So we got 5. They both have in common is 5. And then they both have an x in common. 5x divided by 5x is 1 minus 5x divided from 10xy, saved it, is going to be 2y. These can get much more complicated, of course. We can just throw in a bunch of variables and exponents. We could have more than just two terms. I suppose we can do one more, maybe more complicated example. Sure. Let's factor this polynomial. Let's find out what the GCF is, one part at a time. 21, 14, 49. I'm seeing a 7 in all of those. X squared, x cubed, x to the 4th. Well, the largest common, or the greatest common exponent of x is 2. They at least all have an x squared. You know what? To make things more interesting, I'll remove that y, but I will add on a z squared here. Okay, with all of the x's, we have an x squared in common, so I'll put an x squared there. For all of these terms, they all have a y in common, just one y. Even though this has 3 of them, this has 4, this has only one y factor. So the greatest common y factor is just a single y. Now, what about the z's? Well, these two have a z, but this one doesn't have a z. So the greatest common factors when it comes to the z's is none of them. We can't pull out a z from every single one of these terms, so we don't look at them. They all need to have them in common, all 3 of them. And then we're going to divide out. So 21 divided by 7 is 3. X squared divided by x squared, no x's left. Or y cubed divided by y, or y to the 3rd minus 1 is going to be y squared. 14 divided by 7 is 2. X cubed, x squared is x. And then y to the 4th divided by y is y cubed. We didn't factor out any z's, so that z squared stays there. It's still part of it. And then plus 49 divided by 7 is 7. X to the 4th divided by x squared is x squared. We took out the only y, and then we're left with a z. There. We've factored this.